Hey there, physics students. So in our last lesson, we talked about the kinematic equations. We talked about those four equations that we can use that describe the relationship between displacement, time, initial velocity, final velocity, and acceleration, right? And today what we're going to do is we're going to talk about kind of a special case of using those kinematic equations. We can use those kinematic equations when it comes to objects that are in what's called free fall. Objects that are moving, either thrown straight up or falling straight down under the influence of gravity, right? And so today we're going to talk about falling objects, and our target is still to be able to use those kinematic equations to solve problems. So let's go ahead and let's talk about some of those things, and we'll do a problem. Alright, so all of the things that we've talked about in this unit so far are examples of what's called one-dimensional motion. It's an object moving in a straight line, right? We could be talking about things moving, a car moving this way or whatever, right? But here today, talking about falling objects, this is still an example of one-dimensional motion. If you think about it, if you take an object and drop it, it's going to fall. It's going to move in a straight line, straight down, right? If you take an object and you throw it straight up in the air, well, it's going to move in a straight line, right? In one-dimensional motion. So what we're talking about here today is still objects in one-dimensional motion, and so all the same rules that we've talked about for any other kinds of objects are still the same. Okay, now objects that are falling under only the influence of gravity, we say those objects are in free fall. Okay, normally here on Earth, we don't really observe the effects of really truly free fall because we have an atmosphere, and what that air does as objects are falling through it, it puts resistance to that motion, right? So we usually have another force working on objects other than just gravity, and that's air resistance. But for many objects, the air resistance acting on them is pretty small, right? So for a lot of objects, in a lot of situations, we can kind of approximate them as being in free fall, and that's moving only under the influence of gravity, right? Obviously, for something like a piece of paper, if we drop it, it's obviously not in free fall. That air resistance is significant on there. But if I take, let's say a big heavy rock and I drop it from here, then the air resistance on that rock is pretty minimal. It's pretty insignificant, and so we can ignore it and just kind of pretend it's in free fall. We can approximate its motion as free fall, right? Now, when an object is in free fall, we've learned this, it moves under the influence of gravity. And what gravity does to objects is gravity will always accelerate objects. It doesn't matter what their mass is, it doesn't matter. Gravity will provide the same acceleration to any object, right? Usually we'll call this the acceleration due to gravity. We might use a variable a with a subscript g, or we might just use a variable g for the acceleration due to gravity. So if we have a situation where there's an object in free fall, we know its acceleration, right? That the acceleration is this acceleration due to gravity. And we've talked about it before. The value of this acceleration is negative 9.81 meters per second squared. For any object that's in free fall on Earth, other planets have different acceleration due to gravity. But if you're on Earth, any object that's in free fall will have an acceleration of negative 9.81 meters per second squared. So there could be lots of problems where they don't tell you the acceleration, but you can infer from the problem that this is taking place on Earth, and that the air resistance is minimal, so you know the acceleration, right? So it's something you can read into the problem and assume a lot of times, right? All right, let's go ahead and let's take a look at a problem involving an object in free fall. Alright, here is a problem for us to take a look at. It says Jason hits a volleyball so that it moves with an initial velocity of 6.0 meters per second, straight upward. If the volleyball starts from 2.0 meters above the floor, how long will it be in the air before it strikes the floor? Okay, let's go through and let's look at the numbers and decide what they are. This first number I see, 6.0 meters per second. This is how fast it's moving right at the beginning. It even tells me, it says it's an initial velocity of 6.0 meters per second. So I know this number is VI. So let me write down what I know here. This is VI which it says is 6.0 meters per second. Okay. Now, moving on, it says if the volleyball starts from 2.0 meters above the floor, and let's think about what's happening here, okay? It's going to start from 2 meters high, it's going to go up, it's going to come back down, it's going to pass that point where it started and continue onto the ground. So here's my question for you. What's its displacement? How far does it end up from where it started? Okay. Well, if it started 2 meters above the floor and ended up at the floor, then it's 2 meters from where it started, right? The whole moving up and down, besides the point. We want to know the displacement, how far is it from where it started? It's going to end up 2 meters from where it started, but it's 2 meters below where it started. So let's call it negative. Okay. Let's see, what else do I know in the problem here? It says, how long will it be in the air? So the question is asking me to find the time. And I know one other thing. This is an object that's in free fall, and I can assume that this is taking place on Earth, so I know the acceleration. The acceleration is the acceleration from gravity. Which is negative 9.81 meters per second squared. Okay, now we know what all our numbers are. Let's take a look at our kinematic equations, and let's pick one that's going to help us to solve the problem. Okay, now I have VI, delta x, A, and T. Okay. Let me look at my options and see what I can do. The one that jumps out at me, delta x equals VIT plus 1/2 AT squared. Okay, let's put the numbers in there, and just a little preview here. There's a little trick I'm going to do, and I'm going to tell you about it. Okay, let's put the numbers in here and see what happens. Okay, do I know delta x? It's negative 2.0. Do I know VI? It's 6.0. And then T, I don't know. A, we know. Negative 9.81. And T, we don't know. Okay, now here's the thing. That right there is a quadratic equation. I know we're all good at algebra. I know we can all solve the quadratic equation. I solved it using the quadratic formula. But maybe I was never good at quadratic equations. Maybe I'm kind of lazy and I don't want to, go figure out what was the quadratic formula and put all the things in there. There's a different strategy that I can take. Okay. You can very well solve this quadratic equation and get the answer. I did, right? But here's another strategy you could take. Okay, now I see this and I'm like, I don't want to solve that. So what I'm going to do is I'm going to find something else. The question asked me to find time. Well, let's find something else. I know VI, I know delta x, I know A. What's the other thing? There were 5 different kinds of things that we're working with, right? Here's 4 of them. What's the 5th one? The 5th one was the final velocity. Let's try to find that. And then we'll do a little trick. Let's try to find the final velocity here. Okay. Now what equation am I going to be able to use to find the final velocity? I need something that's got VF, A, delta x, and VI. Which equation is going to be good for me there? The one that does not have a T. I gotta find my equations here. VF squared equals VI squared plus 2A delta x. Okay, let's use this equation and we will find VF. Okay, So VF squared, VI, 6.0, 2A is negative 9.81, and delta X is negative 2.0. Let's work this out and see what we get. So VF squared, let's see, 6.0 squared is 36. And then I'm going to grab my calculator, and I'm going to work out 2 times negative 9.81 times negative 2. Let's see, and that'll come out positive. And with, let's see, 2 significant digits, I get 39. Here, 36 plus 39 is 75. VF squared. So what I'm going to do is I'm going to take the square root. Okay. So VF, now keep in mind, when you take the square root of a number, there's 2 answers, right? One positive and one negative. When I do the square root, the calculator, what do I need? 2 significant figures? The calculator says 8.7. We got to think about which answer is going to make sense. Should it be positive 8.7 or negative 8.7 meters per second? Remember, the positive or negative is a matter of direction. So I expect this final velocity to be in the upward direction or in the downward direction. Okay. Well, if it's striking the floor, its velocity should be in the downward direction. So I'm going to choose the negative answer to be the correct one, right? So the square root of 75, I'm going to say negative 8.7. That's the answer that makes sense. Okay, so now I know the final velocity, negative 8.7 meters per second. Okay, now I'm going to go on and I'm going to go and find what they asked me to find. I got more options that I can use now, right? Because I have another thing. So let's pick another kinematic equation that maybe won't lead us to a quadratic equation that can now involve the final velocity, and we'll find the time that they asked us to find. Let's pick VF or VI plus AT. Let's use this one. Okay. The final velocity I know now is negative 8.7. The initial velocity was 6.0. A was negative 9.81. And T we don't know. Okay. Now let's solve the equation. We'll solve this equation and we'll figure out what we're looking for here. So what I'm going to do is I'm going to subtract that 6.0 to the other side. So that will be negative 14.7. And we have negative 9.81 times T. And then we'll divide both sides by negative 9.81. So T equals, let's see, it looks like we need 3 significant digits here. So I'll say 1.50. And that's a time. Time is measured in seconds. So you can see there I avoided solving that quadratic equation. I could have, and if you'll notice, I got the same answer. Or I could find the final velocity first and take a different route, right? So there's a couple of routes that you can take to find the answer there. Now, will you always have to take a weird route to get there? No. Can you solve the quadratic equation? Yeah. Will you always be faced with a quadratic equation? No. Maybe you'll end up using one of the other kinematic equations, and it'll be really straightforward and simple, right? But, here's a slightly more complex problem, kind of involving those same kinematic equations. All right, kind of a fun problem there. So we talked a little bit about falling objects and objects in free fall. We've talked about the acceleration due to gravity. That's going to be an important number going forward in physics. We're going to be using that number for a long time, right? There's very frequently objects under the influence of gravity on Earth, that we're going to need to know the acceleration due to gravity. So commit that number to memory, negative 9.81 meters per second squared. Hopefully that helps us to be able to use those kinematic equations to solve problems. So until next time, take it easy.